Can you hear me okay? Is it good, the level?
Yeah.
Okay, excellent.
Okay, so we have started recording as well. So yeah,
Excellent.
we can start. Yeah, so welcome everyone for the second online Ruby meetup. This time we have Samuel Williams from New Zealand. He's part of the Ruby core team. He has worked on a lot of things related to concurrency and scalability in Ruby. He has also developed a web server Falcon, as well as a lot of async related libraries. So he's going to talk about some of the tools that he has built, and feel free to ask any questions if you have. Like you can type in the chat. If you're speaking, just say your name and ask your question. And yeah, enjoy the talk. Thanks, Samuel, for joining us and showing us what you're building on.
Excellent. Thank you for inviting me. It's really awesome to be here and to share the things that I've been working on. Samuel, as you heard, and I'm a member of the Ruby core team. So I work with some of the other developers. There are people all over the world working on Ruby. Obviously, there's a lot of them in Japan, and occasionally we meet up in Japan, which is a lot of fun. And so today I'm going to talk about Falcon, which is an asynchronous Ruby web server. Right, let's see if this presentation works. So my first question, is Ruby fast enough? A huge amount of work goes into making Ruby faster. We have improvements to the garbage collector. We have implementations in C and Java. We have variations like Crystal, which explore native compilation. We have the compacting GC, I mentioned that already. And yet, performance is still something that we are trying to improve. And we try to improve performance because it can save money. We can reduce the hardware costs if we need less hardware to serve the same number of users. And if our systems are faster, then they're also more responsive for our customers, which is a great thing. So to understand the nature of Ruby's performance, let's have a look at this hypothetical network request. So this is a 200 millisecond request. It could be a web request, it could be an email system, it could be whatever system you can imagine. And it does 10 milliseconds of processing. And so that 10 milliseconds is actually executing Ruby instructions inside the virtual machine. And it does 190 milliseconds of waiting. And so what I mean by waiting is it could be reading some data from the network, it could be reading a file system. It's very typical. And we see this in things like database queries. So when you have a database query, you might send your request to a database server, and that needs to do some processing. It could be a big analytics query. It could take 2, 3, 5, 10 hours, potentially longer. And so you're waiting for that query to complete, and then you're going to read the result back and present that to the user. In some situations, you have database queries which generate lots and lots of results. So you may have a query that generates 1 million rows, and you need some efficient way to save that for the user. Another example of places where we wait, HTTP requests. So this is very common in web applications. And one example that I was working on recently was the fraud detection for credit card transactions. And it turns out that credit card companies, they interface with lots of third-party systems to do the fraud prevention. So they ask things like, is this a valid credit card number? Does this transaction look suspicious? And all of these are often done over the HTTP request response, you know, a RESTful API or some other interface. And so we might spend a lot of time waiting for that system to process our request and send us a response back. And another example of commonly waiting message queues, where we could have background job processing, WebSocket client and server is sometimes done through message queues. And so putting messages into the queue and waiting for messages to come off the queue, you might potentially spend a lot of time waiting. So let's make Ruby 10 times faster. let's take a look at our hypothetical request. So we reduced the processing time from 10 milliseconds to 1 millisecond. That's a 10 times improvement. But we were still spending 190 milliseconds waiting for the I/O. And this couldn't be reduced just by improving the performance of the VM. So what about if we make Ruby 100 times faster? Now, I'm sure you can imagine what this is going to look like, right? There's basically no change. It doesn't matter in this particular example how fast we make Ruby. Beyond a certain point, the dominating time is because we're waiting on I/O. So let's take a look at the single request and consider, how do we make Ruby faster? So here's our original timing, and we're going to look at this in the context of a web server. So here's our request. The blue part is the processing time and the green part is the waiting time. And obviously this can be interleaved in a different order, but I've just done this for simplicity like this. And so here's our server, which is processing multiple requests sequentially. And this is common of servers like Unicorn, Puma, where, for example, with Puma, you have a cluster with 16 workers, and each worker is processing requests sequentially. And so what that means is, in the case of Puma, you cannot actually process more than 16 concurrent requests on a cluster with 16 workers. If someone sends a 17th request, it will wait until one of those workers is freed up. So we want to take this. What if we can change this? We have our total latency as the sum of all the individual requests that we process. What about if we reorganize our work like this, so that we interleave the waiting time and the processing time, so that while one request is waiting, another request can start processing? We could greatly reduce the total latency and improve the throughput. Obviously, the individual request latency is not reduced, but the total latency is improved. So how can we achieve this? Should we use the multi-process system? How about multiple threads? Ruby has a number of servers which take these approaches: Unicorn, Puma, Passenger. Unicorn is the multi-process web server, and so it makes one process per processor on your computer or your server. And so if you have 8-core server, then you can handle 8 requests simultaneously with Unicorn. Puma is much the same. It makes one thread per worker, and often the worker is 2x the number of CPU cores. So in this case, if Puma has 16 workers, you can handle 16 requests in flight. And Passenger has 2 modes, a free mode and a paid mode. And the free version of Passenger is the same as Unicorn, and the paid version of Passenger is the same as Puma. So who wants to program with threads? And this is an XKCD comic I ripped off. If you're having scalability problems, I feel bad for you, son. I got 99 problems, so I used threads, and now I have probably 100 M's. And this is what happens when you use threads. When you try and write to standard out from multiple threads, the output is interleaved. And while this particular problem is not that common, I've done code analysis on Ruby code. I looked at the top 10,000 gems on Ruby gems by download count. And I took those gems and I downloaded all of them to my computer. And then I ran some basic source code analysis, some regex, and a few other bits and pieces. And we found a ton of issues. And I'm sure there's more that we didn't uncover. So it's a little bit scary. So how do we build scalable web applications? Let me introduce Falcon. Falcon is a pure Ruby web server. It supports HTTP1, HTTP2 with TLS with 0 configuration. Here is a block diagram of how Falcon works. It's built on top of async HTTP, which provides the asynchronous HTTP client and server. And that in turn is built on HTTP protocol, which provides HTTP1 and HTTP2 support. And while we don't have any prototype implementation of HTTP3, it is planned. I'm really excited actually about that. Async container provides the model of parallelism. So it's either forked or threaded. And the reason why we do this is because JRuby and Truffle Ruby do not support forked processes in the same way C Ruby does. And so we have this async container, which basically abstracts that all out of the way. Then we have async IO, which provides the IO primitives and the OpenSSL wrappers, which does the TLS for HTTP2 and HTTP1 if you want it. And then that's built on top of async, which provides the fiber-based concurrency. And that utilizes NIO for R, which uses libev for doing the efficient event-driven IO. And that all sits on top of Ruby and Ruby's fiber implementation. So Falcon has one fiber per request. And this allows us to interleave the requests. So each one of these boxes, in this case, represents one fiber. And so we can interleave those requests when they're doing a database query or some other like long-running task. We can wait and do some other request while the first one is waiting. We use multiple processes or threads per instance, but each instance is completely isolated. And so we have one instance on one processor, which is running this event loop, which is handling multiple requests. And to scale this up to utilize multiple processes, we just duplicate these instances and we can support as many processes as required. And so this is how we build a scalable system with parallelism and concurrency for Ruby. So as I mentioned, Falcon is built on top of async, and that provides the event loop, which is a really critical part of the whole system. It's the fiber-based concurrency, which provides task-based execution, and those tasks execute synchronously, so your code actually doesn't change. One of the problems with async await in other systems like JavaScript is that in order to utilize the improvements to concurrency, you have to change your existing code from the callback design to the async await keywords. And so I have a strong feeling about this actually, that I don't feel it's realistic to ask people to rewrite their code just to make it scale better. And so one of the critical pieces of async is allowing existing code to execute in a more scalable way. And we use fibers to achieve this. The async provides the non-blocking event-driven reactor, and it has a really small footprint. The core gem is less than 1,000 lines of code. Lately, I've been looking into async as one of my projects would really benefit from non-blocking IO. It's really beautifully designed. Janko Moronic on the general design of async. So the question we should all ask now, does it make Ruby faster? For IO-bound work, it scales very well. Obviously, it will depend on your specific use case, whether you have an IO-bound problem or a CPU-bound problem. But in this benchmark, I was comparing the asynchronous database query between Falcon and Puma. And Puma has the cluster size of 16 in this benchmark. And so what you see is that up until 16, they perform the same because the CPU is available and the task is available. In this case, in Puma, it's workers, and in Falcon, it's tasks. But once you hit your limit of 16 in Puma, Puma can no longer scale. The CPU is not pegged, but it cannot continue to improve the number of requests handled. Because Falcon can keep on making tasks, it continues to scale up according to the CPU's availability. Recently, I worked on another project. This is on the client side, the GitHub changelog generator, and it was using Faraday, and they were trying to improve the performance. They had a pull request to use multi-threading, and that pull request was buggy, understandably. And so I got asked by a friend, can I take a look at this? Like, what's going on? And I just said, okay, this is an interesting problem to solve. And so I looked at the pull request, I looked at the problem they were trying to solve, and I thought, this is an interesting problem. it's essentially a problem of concurrency, because what they were doing is they were pulling down all the issues and pull requests from GitHub. And each issue and each pull request requires one web request. When you do a web request to GitHub, it could be 100 millisecond, 200 millisecond, 300 milliseconds. And for one project, you could potentially have hundreds, if not thousands, of these requests that you would need to do to get the information to make a changelog. And so if you can run all of these requests concurrently, you can see a massive improvement. Now, I couldn't improve every part of this gem. I just focused on the parts that I thought were most interesting. But we made a pretty impressive performance improvement on this. This is quite a small repository, and we saved about 50% of the time just by using async HTTP Faraday, which is an adapter which you can drop into an existing project that uses Faraday. So that was quite a cool case study, and I enjoyed that. One other one which was even more impressive was, sorry, my bad. Travis RB and using Faraday. So there is one of my friends had a Travis build matrix. Travis, if you don't know, is a continuous integration platform. So you push your code and it will run your code, your tests on a bunch of different configurations. And he had a build graph which had 60 jobs. Now, if anyone uses Travis, they know 60 is quite a lot of jobs to have on one build matrix. And he needed to pull down the status of those individual jobs. And so the API was quite slow. And he was using, I think it was Typhoeus, another one of those sequential HTTP clients. And he just changed it over to use async HTTP Faraday, and he saw almost a 10 times improvement just because we could improve the concurrency of all those requests happening. So it's a really interesting case study. There's potentially like room for improvement on existing tooling. And what this, in particular, what this shows is few modifications were required to the original code. Dropping in async HTTP Faraday does not require like modification of the original code to see improvements and benefits. Obviously, to maximize the improvement, you probably want to restructure the code a little bit, but the point was also to show that it's possible to use it on existing code without actually having to make changes to the code itself. Async is the right model because web applications are almost always I/O bound. The Ruby web ecosystem is really lacking in scalability, e.g. WebSockets on Puma. Async unlocks the next tier of scalability in the most Ruby-like way possible. Brian Powell on migrating from Puma to Falcon. So a good model for concurrency makes it easy to write correct and scalable programs. And that's what I've tried to build. Does it work with Rails? Yes, it's Rat compatible. Falcon, and a synchronous Ruby web server. So that's the end of my presentation. And what I would like to do now is give some demonstrations of Falcon. So I have, let me just get rid of that. Oh, excellent. So one of the things which was interesting to me is Falcon was experimental for a long time, and I was not confident about putting it in production because it was something which putting a web server in production carries a lot of potential issues. It's an easy target for being attacked, but here is Falcon running in production right now, and let me just make this a little bit bigger. So this is Falcon Virtual, which is a virtual hosting solution for multiple websites. And the main interesting points are we have Falcon Virtual running at the top here. And Falcon Virtual manages two main points. The Falcon redirector, which implements the HTTP to HTTPS redirects. And so by default, Falcon Virtual encourages you to use HTTPS. And then we have this thing called the Falcon proxy. And what the Falcon proxy does is it's actually the main entry point for web requests. And the Falcon proxy will receive the public web request, and then send it off to one of these application servers back here. Now, these application servers, they're robust. So I can go in here and I can kill this. Let's kill it, and hopefully it comes back up. So there we go, it came back up right there. And so this is the kind of rolling restart mechanism, isolation that keeps your application safe and prevents issues. Now, most major web servers have this. It's not unique by any measure, but it was quite a cool thing for me to have in production and see it all working. I was happy. And I'm going to show one other thing which I think is kind of cool, and then we'll go to questions. So one of the interesting things to me was looking at the scalability issues of existing web servers. And I was not particularly impressed with Ruby's ecosystem. Actually, I'm going to detach this and put on a separate. Give me 2 seconds to get this organized. And I'm just going to kill that and that so I can restart them. And I'll make that one bigger. Okay, so on this side, this is a demo of Async WebSocket, which is the WebSocket client and server implementation built on top of Async. And you can run this inside Falcon. So the server is actually Falcon, which runs on top of Rack, and then you can serve WebSockets. And so we're going to go ahead and we're going to run the server. Actually, I need to use bundle exec. So that's Falcon running there. It's running on my local system. I just might make it slightly easier to fit in there. And then over here, I'm going to run the client. And the client is going to make as many connections as I want. So I want to make, -C. So let's make 100,000 connections. So this is Falcon. It's running one container, one instance. So this is, my computer is actually quite old. It's almost 8 years old. I have 16 gigabytes of memory, and I have a 4-core Intel CPU. So it's not really that powerful. And one of the reasons why I wrote this benchmark is because I'm interested in the garbage collection performance of Ruby. And this is a test which tries to really punish the garbage collector. And so we are making currently 1,200 WebSocket connections per second. And that's over HTTP2, which I think is over TLS as well. So it's actually negotiating OpenSSL, TLS connection, HTTP2, and then making the WebSocket connection through a long-lived web request. So we're up to 40,000 connections, running at 1,138 connections per second. I'll just pull up htop. And I want see if I can find the process. Let me just order by memory usage. My Zoom, awesome. Okay, there we go. So this looks pretty crazy. We've allocated 55 gigabytes of virtual memory. It's still going up. But actually, the virtual memory is irrelevant. What's really important is the resident set here. So the server is currently using 2.3 gigabytes, and the client is using 1.9 gigabytes. Oh yeah, we're finished now. So we've got 100,000 connections, and we're using 2 gigabytes of memory. Now, if you do the math, you'll find that's pretty good per connection overhead, pretty small. By good, I mean small. And so this is, for me, this was like quite an impressive benchmark. So these are live connections. They're sitting there. If you send data to them, they'll all ping and pong and communicate and so on. And so to me, this was an interesting test case. And in particular, the garbage collector has seen massive improvements over the past couple of releases of Ruby. The last GC was 0.51 seconds. That's quite slow. It's 500 milliseconds for one GC. But it used to be like 50 seconds. So like, it's a big improvement. And most of that goes, the credit for that goes to the core Ruby contributors, Koichi, Aaron Patterson, and a bunch of the other guys who are working on it, doing a really incredible job. So look, that's the demo that I was planning. I'm happy to do some coding as well. If anyone has a question that relates to coding, I'm happy to like whip up some examples. I've got tons of example code. So I'm happy to open the floor now for questions. Sorry, you're still on mute.
Oh, sorry. Yeah.
It's
So
okay.
saying, Sanand is asking in the chat about the localhost loopback effect.
Yeah,
that's me. Yeah. So would the loopback affect the benchmarks here? Like if we ran it over like a subnet, maybe?
Absolutely. So there's lots of ways you can do benchmarks. The way that I've heard is the best way is to have a real network with two separate like systems and then run a real benchmark between them. So like the client would be on one system and the server would be on another system. So obviously there's, with any benchmark, you always have to take into account the nature of the benchmark. That being said, the benchmark here was not so much the nature of the network performance, but it was more looking at the scalability constraints of the server. So like one example was when I first wrote this code, async WebSocket, I used Faye WebSockets, FAYE-WebSockets. Like a lot of people use it. And that code allocates like 400 or 500 objects per connection. In order to make my code this code can do 1 million connections on the system. It just takes a while. So I didn't want to like wait everyone for 1 million connections to happen. But if you do 1 million connections and you allocate two times the memory, instead of being like say 20 gigabytes, you'll be 40 gigabytes. If you allocate 3 times the memory per connection, instead of being 20 gigabytes, you'll be 60 gigabytes. So the problem is, when I first wrote this code, I used Faye WebSocket and it was allocating tons of objects per socket, and I could not do 1 million connections on the system. So I rewrote it and I optimized the memory allocation, and I got it down to like 70 objects per connection, 60 or 70 or something like that. And then because of that, the memory usage went from like 100 gigabytes down to like 20 or whatever for 1 million connections. So it's kind of, for me, the benchmark was more about like memory usage, and the connection overhead, as opposed to like the real world latency of work, because that's unpredictable. And I think we can all understand that the nature of that is always going to be affected by the network that it's traveling across.
Yeah, makes sense. Yeah, it does. And in fact, I think if we ran the same benchmark over network, it probably would even reveal more performance upgrades because of the IO and other weight. Yeah, potentially.
Potentially, yeah.
Cool. Thanks.
No problem. Good question.
Okay, we have a question from Aditya. When the rubber meets the road when using fibers. Yeah, you can just check the question.
Okay, hold on. How do I see chat?
Somewhere there should be a chat button that I can, or I can read it. Where the rubber meets the road.
Let me just find it. I'm sure I can find it.
On the bottom, there should be like an orange color somewhere. Chat will be somewhere. Yeah.
Because I shared the screen. Oh, here we go. There's a thing at the top of my screen. Oh, come on. More chat. There we go. Okay, I got it. Okay, awesome. Give me 2 seconds. Yeah, good question. So where the rubber meets the road is when using fibers for blocking IO. I recall there was a thread, pun not intended, going on regarding a patch which makes fibers automatically yield on blocking IO. Is that happening? That's a really good question. We cannot solve all the problems of blocking operations, and that is actually built into the design of Falcon right from the ground up. even if you look at memory latency, like instructions on the CPU that do memory operations, like reading from your memory, if the memory is in an L2 cache, it will be faster than if it's in your main memory. Or if you have swap to disk, it will be even slower because you have to load that. You have like a memory fault, you have to pull that data from a disk back into your memory and then into L2 cache before the CPU can use it. So my opinion on this is that all operations, even down to the CPU level, have some level of blocking. And what you have to do is you have to draw the line. Where do you try and, where do you choose to become non-blocking? Like network IO is a really obvious one because network IO has a very high latency. And so by making network IO non-blocking, you reduce the latency of your program by a significant amount. Then you look at things like file system IO or other forms of like blocking down to the CPU level and you think, well, okay, we've addressed one, what can we address next? And so I'm not sure if you're familiar, but there's a new interface for Linux called IO U-Ring. I'll just bring it up. I think I have to kill the server because my computer performance has gotten so bad now. Let me just free up some memory. Hopefully that will make things a bit better. Actually, this PDF sucks. Let me just find a better page. So in a normal system, you have like system calls like read and write. And what IOU ring does is it basically makes a ring buffer for your process. And you put requests into the ring buffer and the kernel reads those requests and puts the results into something called the completion queue. And so there's more than one system call that can go on this, like read and write, sleep, waiting for a process, all examples of system calls you can put in this ring buffer. But for the first time, Linux supports the non-blocking file system IO, which has been incredibly tricky up until recently. And so what this basically enables is for us to take more operations and make them non-blocking. It's enabled by this IOU ring. Now, coming to the next part of your question, which was, there was a patch which automatically yields on blocking IO. Is that happening? And the answer is yes. So the original implementation was written by Eric Wong. And we are not using all of that implementation, but actually we've got a different implementation and it's called the Lightweight Scheduler for Improved Concurrency. And so the way this works, let's make it a bit bigger, is we have this scheduler interface and we have these entry points like wait readable, wait writable, wait any, wait sleep. Then when you write your user code, I wonder if I've got an example here. Yeah, here's kind of an example. So you make a fiber and you tell it that it's a non-blocking fiber. And then these operations like io.read and io.write and sleep, they go into the scheduler. They call this function. And so async provides an implementation of the scheduler. And so what that allows is when you run an async application that's built on top of async, and you have native Ruby IO, async will actually intercept those IOs and make them non-blocking. And so that is, I think, going to be happening for Ruby 3.0. And the goal there is that maybe this is the initial design, but hopefully we can expand like IO right now. If it's a file IO, then it won't give the desired behavior. But this interface allows us to plug things like IOU ring into it. And so like this interface provides the flexibility we need going forward to build the more concurrent Ruby and to make that transparent to the user. I hope that, okay, how will rect by actually change the concurrency to Ruby? Okay, this is a really good question. Sorry, just I hope I answered the previous question, okay? Feel free to ask a follow-up. How will rect by actually change the concurrency story of Ruby 3? Will Falcon async adopt it? So Rector is like it's an interesting model. The rector itself is like a thread, but it's isolated from other Ruby code. So you can't pass shared mutable data into a rector instance. Rectors provide a way of passing messages in and a way of passing messages out. And then internally, those rectors are isolated from other rectors, and they run on separate processes if possible and give you parallelism so that you can run truly parallel Ruby. Because up until now, it was not possible to run Ruby truly in parallel, unless it was like a C extension. When you write a line of Ruby code and it gets executed, Ruby will hold the global VM lock. And so if you have two threads in Ruby and you have you have two loops or some other kind of processing you're doing, Ruby will not allow those lines of Ruby code to execute in parallel on separate CPU cores. But with rector, you put those loops inside individual rectors, and then they will work on separate cores and run in parallel. The contention I have with this design is, firstly, you need to rewrite your code to use rector. It's not something you can just drop into an existing system. And the other tricky part is it's not clear how users will be able to use, like, for example, with C Ruby, rector is the only way to achieve parallelism. But on JRuby and Truffle Ruby, you can achieve parallelism with threads. They work today. So the reason why rector exists is to work around the limitation in the C Ruby implementation. Now, Koichi might argue against that, but I think if we could make threads work in C Ruby as this sort of, as in the same way that they provide parallelism in JRuby and Truffle Ruby, that would actually be a better abstraction because it's consistent across all the platforms that currently work, and users wouldn't have to rewrite their code to necessarily take advantage of it. But the caveat to that is that threads in C Ruby actually have issues with C extensions which are not thread safe. So C extensions assume that they don't need to be thread safe. And therein lies the problem of trying to use existing code and retrofit C Ruby's threads, because by doing that, you're going to break all the C extensions that have any kind of like parallelism. So rector is kind of like a solution that we can't make threads run truly in parallel. And so we'll invent a new concept which allows parallelism, and then we'll need to modify C extensions potentially to take advantage of it. But yeah, it's super tricky. Like you look at Truffle Ruby, they've got C extensions which work with real threads. And so it's sort of, to be honest, it's not really my area. But the last part of your question was, will Falcon Async adopt it? I think, I don't really know yet. The place where it would be most useful is in async container, where we have the abstraction for the multi-threaded or multi-process models. And I guess you could have like a multi-thread model for C Ruby that uses rector instead of threads, or some new model like the multi-rector model. And the benefit of that would be primarily memory usage. So the multi-threaded server versus the multi-process server, the memory usage is potentially a big concern. When you have 16 threads running in one server, that server loads your application code once, and then it is shared between those 16 threads. That's both a problem, like thread safety concerns, but it's also a benefit because the system and the garbage collection, all those things work together to minimize the memory footprint. When you use the multi-process model, what Falcon does is it loads all your application code into the top process, and then it forks off workers. And those workers use copy on write provided by your operating system, and they take a copy of the memory. But the problem is, over time, that memory is modified, written to, and so the copy on write mechanism comes into play, and the individual worker, it modifies those pages of memory, and then its memory usage, its memory footprint increases slowly over time. So it's a tricky one. The benefit of multi-thread is primarily memory usage at the expense of processing throughput. And the value of multi-process is isolation, failure tolerance, rolling restarts. There's a lot of benefits to multiprocess, but the biggest cost is overtime memory usage. So there's no like one solution that is the best solution. It's just there's a whole bunch of compromises. I hope that answers your question.
So in Ruby, there is also a library called as concurrent Ruby, which also has supports for futures and promises. And does async replaces that for async await functionality? Like, does it have complementary feature?
Right, that's a good question. So concurrent Ruby is a library for implementing parallelism in Ruby. And the biggest problem with that is that C Ruby is not parallel with multiple threads, as we discussed earlier. So anything you do with concurrent Ruby, you will still have contention on the GVL. Now, a lot of the time, if you go into a C extension, like say you're doing a Postgres query on the database, the query is a C extension which releases the GVL. And so that does allow some amount of parallelism. But in effect, concurrent Ruby works best on Truffle Ruby and JRuby, where you have real threads. Async essentially provides similar constructs, but the key point for me is that when I did the code analysis looking at the kind of thread safety issues in Ruby, I found a lot of problems. And I found a lot of people, I made pull requests and people were like, oh, I didn't know there was a problem. I thought it would be okay. Or so there's a kind of lack of understanding about what issues are potentially, what things are potentially thread unsafe. And so when I built async, I was trying to think, what is the model that encourages scalable and safe systems? When someone is trying to build something, how do you guide them to build scalable and safe systems? And so async it has a different kind of model. I've called it the N1M model. And what I mean by that is you have async container, which provides isolated concurrency. And then you have one event loop. And then you have multiple tasks. And the critical point is a lot of systems that do the hybrid green threads or whatever, they're NM. So they don't make any guarantees about the scheduling of your work across processes. So you still have thread safety issues. But async ties you down to one event loop in each instance of your container. And so what that means is, as a programmer, your chance of making the thread safety issues is greatly reduced. You can still make issues if you have sequencing problems, but you won't get memory corruption or data corruption in the same way you would if you write thread unsafe code. And so that's kind of my goal was concurrent Ruby's goal was to make a toolbox of multi-threading parallelism primitives. But my goal for async was to build something which guides people on the right direction to build scalable systems. So I wasn't really interested in introducing concepts just for the sake of it. Oh, this is a really useful concept in some academic research or whatever. I was more interested in how do you give people and encourage people to build scalable and reliable software. And part of that is actually limiting what they can do and not giving them all the tools under the sun. Does that answer your question?
Yeah. Yes. So the problem that you mentioned about a lot of libraries having thread unsafe code, can those issues happen also in the application code?
I mean, yes. Multi-threading is difficult. People don't know when something should be thread safe or not. It's not obvious that something should be thread safe, or like a really good example of this is memoization. So when you have a function and you call that function with the same arguments, it's common to have a cache which says, I've done this work before, here is the result. And it turns out that there's actually, I found instances of memoization which were unsafe. So you would have like a global cache, which was shared across multiple threads, and there was no mutex protecting it. So multiple threads could be accessing this cache. There's a video that I did about a month ago where I showed if you do this on JRuby, you'll actually end up potentially crashing. So like, and it's not a problem of JRuby, it's a problem of thread unsafe mutation of data structures. Now there's ways that we can work around that in JRuby and CRuby, but if you do multiple operations like read from check if the cache has something or not, and then compute it and then put it into the cache, it's possible 2 threads go in there and interleave the operations, and you have all sorts of problems. I did a talk at Ruby World Conference, a little bit hard to find, so I'll flick it up on Twitter, a link to it, where I gave an 5 examples of the thread safety issues that I encountered and were easy enough to explain. So that might help answer some of your questions regarding the kind of thread safety issues that people would run into. But these are in gems that had like millions of downloads. So like not that great, not that encouraging to see these kinds of issues, I guess. Does that help answer your question?
Yes.
Hey, hi Samuel, Atul here.
Hello.
I had seen one talk of yours where you had mentioned that you searched into the few code bases of a few gems, and you found out some mutexes issues. Can you share one simple examples where one can get started?
Yeah.
Okay.
So we did the code analysis and we found all of these issues. I don't know which one is interesting or easy to, I don't know if any of these are easy to explain or not. I'll just open up a bunch and we'll flick through.
Can you make it full screen?
Yeah. So this is an example of a cache that's being used incorrectly. So there was just no mutex around it and it could have multiple threads coming in and accessing it. Let's have another look at another one. So this is an example of the mutex that was lazily initialized. And so I gave a specific example of this in my Ruby World Conference talk. But what happens is if you lazy initialize a mutex, if you have multiple threads try and do this, there's a chance that they will all get different mutexes, which is like a disaster. It basically means that the mutex has no effect at all. And so the solution to this is to make sure that the mutex is not lazy initialized. It's put in the initialize method of the class itself, and then it's utilized accordingly. This was a surprisingly common error. I think most of these are actually that particular issue. So this one also was lazy initializing the mutex. And so we just changed that, whether the system is multi-threading enabled or not, that creates the mutex. So it's a kind of surprisingly common problem. And this was just one class of problems that we could easily identify. That's why we found so many of them. So this one again had the lazy mutex initialization. Lazy mutex initialization. Lazy mutex initialization. I can go on. But I think you get the point, right? Like, I mean, does that help answer your question?
Yes, thank you.
You're welcome.
So in the demo, you had shown like 2-3 applications were running on the same server. So how was that possible? Like one Falcon server was handling different multiple applications, or was it something else?
Yeah, so Falcon Virtual is, it's like a virtual hosting system like Nginx, for example. So one of my goals for Falcon is to replace Nginx. I still think that it's good to run a load balancer in front of it, but I see a lot of deployments where you have a load balancer going to a server which has Nginx and then like Passenger, Puma, or Unicorn. And in my opinion, there's no point to have Nginx there. It's really, it introduces like extra latency that shouldn't be necessary. So let's have a look at, I've got some really crappy ASCII art diagram. Where did it go? Maybe it's this one. No, it's not that one. So this is the Falcon virtual ASCII art. And so you essentially have the browser, and it's communicating with the Falcon proxy, and then Falcon proxy is communicating with the application server. And so the application server, there can be lots of application servers, and Falcon will manage them for you. And so like if you have like, say, a virtual host where you might have like 5 or 10 or 100 different domains, Falcon can spin up all those application servers for you and manage them, restart them, rolling restarts, deployment or whatever. It works really great. Like, I mean, I've been using it in production. I haven't had, there were a few initial issues because the code was never tested before in production. But once those have been, I have had it running in production for like a month or maybe longer now. So, I'm pretty happy with it. It hasn't been hacked yet, so that's a good sign. So yeah, basically Falcon will manage applications for you, multiple applications, and the Falcon virtual mode will spin up model applications and proxy to them. Does that answer your question?
Yeah.
We have one question with from Akshay in the chat.
Yeah.
Can you share your experience about? Yeah.
Oh yeah. Can you share your experience about how you got started with Ruby concurrency? How should beginners start learning about concurrency in Ruby? That is a really good question. When you write a computer program, the most important thing is that it works. Scalability is not a concern until you have made a program that works correctly. So in my mind, concurrency is not a feature of your code, but it's a function of the server. When you write your code, whether it runs on one processor or 100 processors, provided you are doing something like a web application where you have this kind of request response model, there shouldn't be a need for you to write explicit concurrency or parallelism into your program. Now, that gets a bit more complicated when you start doing things where you actually need parallelism, which means you might have a process where divide and conquer makes sense. And by divide and conquer, I mean taking a piece of work, breaking it into separate pieces, and running those pieces individually on separate processes. To understand and learn about that, I mean, the place where I learned about that was at university. So I did the courses on C programming, and I don't think they did a good job of teaching it because, like, I guess no one really knows how to teach threads in university. I mean, sorry, that's a little bit rude, but it's not a topic which is taught in the mainstream, I guess. So in terms of concurrency and parallelism, really, in my mind, in the design of async was to enable people to write the correct program and then make that program scalable by deploying it on an application server like Falcon. Then again, like once you start looking at parallelism and concurrency in terms of actually writing computer programs that utilize parallelism to solve the problem, that is a deep topic. And I don't have any particular advice from where you should start, but the best place is probably things like the dining philosopher's problem. Merge sort is a really good sorting algorithm which you can split across multiple CPU cores and do it really efficiently. There's a couple of different algorithms which will teach you the ideas about how to use multiple processes to make an algorithm faster. But again, like, I don't think most people should be doing that. I think, like, in terms of scalability, write your program, write it correctly, and the application server should take care of the rest. that's kind of my opinion on that point. I hope that answers your question. It's not a very good answer, to be honest.
Samuel, you also worked on OpenSSL gem, right? So
yeah,
can you tell us a little bit about it? Like, what problem does it try to solve?
right. So when you send your credit card data over the internet to make a purchase, hopefully the information goes to the right person and not the wrong person. And part of this is encryption. And the most interesting demonstration of encryption I ever had was in university, actually, where we had a physical compact disc case with 2 locks on it. And it was a demo to show that you can pass data between 2 people without the data being revealed. And the way that it worked is someone has the CD, like a book or case, like something containing data, and they put their lock on the case. And then they pass it to the third party, like the network, and then the network delivers it to the destination. And that person then puts their lock on the data. So now that it has 2 locks on it. And then they pass the data back through the network to the original person. And the original person takes their lock off. It only has 1 lock on it, the lock of the destination. And they pass the data back through the network, and then the person receives the data and they can unlock their padlock. So the idea of encryption is a way of passing your data through a network and knowing that the data is not visible to the network. And there's a lot of different ways you can achieve this. And the most common library for doing this is OpenSSL. And OpenSSL is a C library. And it has been around for a very long time. Actually, hold on, what the sidebar say. When was it first released? Wikipedia might know. It's 22 years old. That's quite a long time for a piece of source code. And so OpenSSL is the implements that locking mechanism and others. In order for Falcon to utilize SSL, we use the Ruby wrapper for OpenSSL. And so what this gem does is it provides the Ruby wrapper for the OpenSSL, which lets us do the encrypted client-server communication. And so Falcon uses OpenSSL on the server side to ensure that it can process HTTPS requests, because those requests are encrypted. In particular, HTTP2 requires encryption. So it was not possible for Falcon to support HTTP2 without encryption. I can give a really quick demo of what that looks like. Let me just bring up a terminal. Just give me 2 seconds. So here's a really simple example of a REST application. All it does is serve hello world. That's literally all it does. And if I run Falcon serve, it doesn't work. So Falcon is now running and it's serving over HTTPS localhost 9292. And so it says not secure because it's a self-signed certificate, but it is working and it's HTTPS and it's HTTP2. So this is a nice solution for Ruby development, because if your development environment is HTTP and your production environment is HTTPS, there's an inconsistency and that can lead to problems. I've seen that literally lead to problems where someone is pulling in JavaScript or CSS or some other asset from the insecure host, and in development it looks fine. They push that to production and it doesn't work. So Falcon essentially allows you to run your local development environment using HTTPS, and that happens through OpenSSL, and that's required for HTTP 2. Does that answer your question?
Yeah. Do we have any questions? Feel free to ask anything. We have Samuel today.
Samuel, hi Atul again. You had faced some issues with the money gem. Can you share about it?
Yeah. Let me just see if I can find. I did make a pull request, and I think it got merged. I don't know if it was in this gem or one of the related ones. Right, so this gem, they were using a mutex. And they also had a Boolean variable called inTransaction. The original code had this method called transaction. And if inTransaction was true, or the class was running without a mutex, it would yield, it would execute the user code. Otherwise, it would lock the mutex, set inTransaction to true, call the user code, set inTransaction to false, and then return the result. Now, there's two issues with this. Let's say we have two threads that enter this code. Thread number 1 comes in, and it sets inTransaction to true. Now let's just stop thread 1 there. Thread 1 is stopped now, and thread 2 comes in this code. Now inTransaction is true, and so it doesn't lock the mutex. It goes straight back to the user code. So there's no synchronization. So now we have two threads potentially reading and writing to the same hash table. On JRuby, that can be a crash. The next problem with this code is that what happens if the user code throws an exception, right? We never hit this line, right? And so then this is always true, no matter what. So there's no synchronization. So if this code was to somehow throw an exception, the one that is reading and writing, then from that point on, the synchronization is completely gone. So this is a kind of tricky issue that I don't want to criticize the original author of this code, because actually they made an open source gem and they gave it away for free. So I'm not entitled. They don't owe me anything or anything like that. But the reality of the situation is they made code that lots of people use, and that code is fundamentally wrong in a way which could cause critical problems in money handling. So it's not good for Ruby as a whole, as a community, to have code like this. We need to fix it. So that's what we did. And now the problem is fixed and it's good. But I think it highlights the issue that users struggle to write thread-safe code. They struggle to understand the issues and the kind of problems that could happen when you interleave the execution of multiple threads. It is, even for experts, it is not easy. Does that answer your question?
Yes, it does.
Excellent.